Okay, so in the last lecture, I had introduced to you the basic steps of the damage locating vector approach to do damage localization, in which case we were working with changes in the flexibility, right? Now, the lecture today is going to be on how you can extract the flexibility matrix from measured vibration data. Of course, the flexibility matrix has a very clear definition in terms of statics, right? So if I have a structure, let's say we use our shear buildings for illustration. If I have this structure, actually let me put one more floor, and I want to know the flexibility defined in terms of these two coordinates, the coordinate 1 and 2, let's say. Okay, notice that I'm not using all the degrees of freedom because in the end we are going to be defined by the location of sensors only, right? The coordinates are defined by the sensors. So let's say that I want to talk about coordinate 1 and coordinate 2. Then the flexibility matrix for those two coordinates, it would be simply F11, F12, F21, and F22, right? That is a very simple, clear definition. If I want to know F11 and F21, I just come here, apply a unit load, right? We're going to use kips because conventional. And when I apply that unit load, my structure deforms. So it deforms like this, then it deforms like this, if it's a shear building. And this deformation here is the deformation at 1 due to a load at 1, and this one would be the deformation at 2 due to a load at 1. So from a point of view of illustrating what it is in terms of statical computations, or if I had a model of the structure, there's nothing to it, I just calculate the coefficients, right? If I want to think about it experimentally, then you could say, well, okay, experimentally I will come here and I will apply a load, but how are you going to do that in a real structure? How are you going to get this unit load statically applied horizontal at this level and so on? It is generally impractical. You can't do it. Okay? I mean, I guess you could, if you don't have any limitations on practicality, right? You could do it because you could set up some sort of a system, right, of pulleys and whatever. You could say, I'm gonna do something here that attaches like this. I'm gonna construct a structure here, you know, of a tower that is attached to the ground, and then I'm gonna go like this, right? And here I'm going to put my one kip, right? And so if I do that, this thing is gonna pull with one kip, and then that's it, I did it. But imagine this contraption just to apply a load horizontally, right? So that is just not gonna go. So what we need is a way to extract the flexibility matrix at the coordinates when all we can actually do practically at best, because here we're still under the constraint that we must be able to apply loads at will, is that we can measure vibrations. Okay, so I may be able to do this, right? I may be able to come here and apply a shaker here, right? Which uses inertia, and this shaker has two masses that rotate in opposite directions and so on. And by applying this shaker here, I can create a dynamic force F of t at this level, right? And then I can measure my, for example, accelerations here, right? Y double dot, and maybe my accelerations in this level also, Y double dot, right? So that may be okay. I could probably measure without too much difficulty my acceleration at level 1, what I called 1, acceleration that I called 2, and perhaps measure, because I am controlling the shaker, what this load is. And what I need to do is figure out how I can take this information and extract the flexibility matrix that I cannot really do from the static case. If you can actually do in any particular problem in a setup, if there is a setup in which you could actually do the problem statically, that is, you could physically, practically apply a static load, then that's the way to go. That's easier. And not only easier, it's going to end up being more precise for reasons that will become apparent to you if you develop sufficient experience on this thing. In the case of the static computation, you have basically computed the actual flexibility. In the case of the dynamic, you are only going to be able to compute the contribution to the flexibility of the identified modes, and in many cases you cannot identify all the modes, so there is going to always be some sort of approximation in the flexibility estimated dynamic. Okay, so that's the setting. Now let's begin by taking a look at some relations. The theory takes a little bit, it's not too much, but it's also not trivial. It's not 2 steps. So let me start by describing a system that is linear in state space, like this, right? Having an output equation in which I'm going to use the subscript d to mean that I am measuring displacement. So we're going to take a little bit of a parenthesis here, okay? Before we get back to tie it all together and say, okay, therefore we can do this. Right now, you can just sort of disassociate your attention from the point that we're calculating flexibility and just follow the steps of this analysis as we go. So we have a state space model of some sort of a system that it's linear and time invariant, right? And it looks like this. Now, that would be so if we measured displacements, right? Now imagine that instead of displacements, you measured velocities. Then if you measured velocities, you would have measured the derivative of this y, right? So clearly you can say that if you measured velocities, you would have measured the derivative of that y, and so that would have been CD times the derivative of the state, right? Clear enough? But we know what the derivative of the state is. Therefore, we can say that the measured velocity would be CD times AX plus BF, right? Function of time. And so multiplying, we'd have that y dot is equal to CD times A times X, or times the state, plus CD times B times the load, right? So the output equation, had we measured velocities consistently here, would have been this, right? But we know that if we had measured velocities, the equation could have been written just like this. The output for velocity times x, right? And we conclude, therefore, that these two expressions must be the same. Therefore, we have that CD times A is equal to CV, right? And since there is no direct transmission term when we measure velocity, we also conclude that CD times B is 0. So notice then that the state space matrices here are not really independent completely, right? Because this is a constraint. CD times B must be 0, where CD is the displacement measurement, right? And we also see that if we measure velocities or if we measure displacements, the matrices are not independent. They would be related by the A matrix, right? Okay, then the next step that we do is we can say, all right, how about one more derivative? So if we take one more derivative, and we say the derivative of y dot, had we measured acceleration, what would we obtain? Well, we would obtain CD times A, right, times x dot. This we already was 0, so I won't put it there, right? So that's what we would obtain. Therefore, y double dot, had we measured accelerations, would have been CD times A times x dot. But x dot is AX plus BF, right? Therefore, y double dot is equal to CD A squared x plus CD A B F, right? Had we measured accelerations directly and actually wrote the equation, we would have written that y double dot would be c of the acceleration, right? Whatever the acceleration state to output is, times x, and that perhaps we would have had a direct transmission term that we would write as d times f, right? So from here we conclude then that there is another relationship. That is, we conclude that CA is equal to CD times A squared, right? And we also, interestingly, find the relationship that the direct transmission term is actually given by something that is a Markov parameter, right, for displacement, which is CDAB. So we have in front of us now a number of relationships that we have derived by simply starting with the state space equation and the output equation and looking at the simple derivatives plus the substitution of the original equation. Okay? So what I need to do now, because this board is small, is I need to summarize the ones that matter to move forward. So I will erase the left side here. Actually, no, I'll erase everything because I have them in my hand here. Okay, and then now let's summarize what we had. So we have CD, then we have that CB is equal to CD times A. We have that CA is equal to CD times A squared, right? We also have that D is equal to CDAB, but I'm not going to be using that for our derivation, so I think I will leave it as this to keep things as tight as possible, right? So at this point, with those relationships, we go to our next step. And our next step is to take a Laplace transform of the state space equation. So again, here is the state space equation. X dot equals AX plus BF, right? Now let's see this. Let me put here time so it's explicit in this particular case. And we have Y, which is a function of time. And it depends what I am measuring. Let me just say that I am measuring displacement. And so I have something like this. There is no direct transmission term when you're measuring displacement or velocity, and there is when you're measuring acceleration, provided that the forces are collocated, or there is at least one that is collocated, that is at the same location of an output. Since that's the only way that the output gets influenced instantaneously by the input, with no lag time. Okay, so we have that, right? Now we need to talk about, well, not talk because that would be too long. okay? We need to take the Laplace transform. Now, if you haven't had any exposure to the Laplace transform at all, and maybe there is a couple of you in the class that have not, those that were in the dynamics class did, I believe, get some exposure, and maybe they've had it before. It would not make sense to me here to try to explain it and so on in 10 minutes. That would make much sense. So I will take the executive view, right, as follows. The Laplace transform allows you, for our purposes, to convert equations that have derivatives to equations that do not have derivatives anymore. The transformation is done, or that gain is realized by switching from the independent variable t, which is time here, to the independent variable s, which is a complex number. Okay? And all we need to know is that if we have x of t, for the purposes of this discussion, and we take a Laplace transform, we get something which is no longer a function of t, is now a function of s, where s is a complex number. Also, if we have x dot of t, and we take a Laplace transform, this requires that we assume that there are 0 initial conditions, that is, that this thing begins from 0 and this begins from 0, and we will accept that that's the case in our derivation to simplify. So if we take the Laplace transform of the derivative of something, here is what is useful for us, which is that the Laplace transform of the derivative of something is just the s times the Laplace transform of the something. So this is all we need in order for me to advance. If you don't know anything about the Laplace transform, then you can educate yourself a little bit by going into the web and reading a little bit and you know, learning the ABCs of it if you didn't have a chance to pick it up before. For our purposes, all I'm going to be using is the fact, these two things, right? So, given these definitions, I will now take a Laplace transform of the state space equation, and you will see then that the Laplace transform of x dot will become s times the Laplace transform of x. A is a constant, and the Laplace transform of x is x of s. B is a constant matrix, and the Laplace transform of f, which is a time function, is, instead of being ft, is fs, right? Now from this equation, notice no more derivatives, just pure algebra now, right? So we can say that this is the same thing as having the identity matrix multiplied times s, minus the matrix A, which I brought to this side. These are both multiplying the vector xs, and they must be equal to b times fs. Okay? From where it follows that the states in the s domain, in the Laplace domain, is equal to identity times s minus a to the minus 1 times b times fs, right? So here we now have a connection between the state and the load that is purely algebraic, right? Here what we have is a relationship between the state and the load, which is a differential equation, but this is purely algebra now, right? Now, if we take a Laplace transform of the output equation, we would find that y, instead of being y of t, becomes y of s. CD is a constant matrix, and the Laplace transform of xt becomes just xs, right? Since we have an explicit formula for xs, we can plug it into here, and we get that ys is equal to cd times identity times s minus a to the minus 1 times b times fs, right? So we now have the following. We have a connection between the load and the output, which is purely algebraic, provided that we talk in the Laplace domain, right? So from the point of view of, let's see, how do I say this? If you have a spring, right? It's for those of us in structural engineering. If you have a spring and you put a force F, right? And the spring has a stiffness K, what happens to the spring, right? It gets longer. And it gets longer by an amount delta. Where delta is the force over the spring constant, right? Okay? Or, if you'd like, we can write delta is equal to 1 over k times the force, right? So, compare that to this. This is how much something is moving, and this is the force, right? It's exactly the same thing. Except there is no Laplace here, but this is just the same thing in the Laplace domain. Y sub s is equal to this f sub s. Now, I can go even further. I could say that, let me see, I think I need this one, but I don't need this. In fact, let me be a little bit more general before I move onward. In the case of statics, right, we know from our basic training, that the stiffness matrix of a structure times the displacements are equal to the vector of forces, right? That if you invert that, you get that the vector of displacements is equal to the inverse of the stiffness matrix times the vector of forces, right? And that you can write that, if you'd like, by saying that the vector of displacements is equal to the flexibility matrix, because the inverse of the stiffness is the flexibility, times the vector of forces. Not to confuse with the F, right? Okay, now, if you come here and you take S equal to 0, then you would find that y at s equal to 0 is equal to minus cd times a to the minus 1 times b multiplied times f at s equal to 0. And it turns out that y at s equal to 0 is the static displacements, and f at s equal to 0 is the static forces, that in the sense that we looked at here. So in a very simple manner, we have here an equation for this matrix, which is the flexibility matrix. That's not going to be, if it were just that, then this would be very easy. But we will see that there is more to it, right? It's going to take a little bit longer. Why? What is the issue? Well, first, or most importantly, the issue is that when I wrote this here, I'm talking about we are measuring all the coordinates, and therefore this is the complete stiffness for all the coordinates, this is, and so on, right? This is the complete flexibility with all the forces. If I only had some values of lambda, okay, as long as the forces are only in the particular locations where I'm also measuring, that's not a problem. Let me see, maybe that requires clarification, maybe not. I don't want to stray too far from the path. So let me not do that. Let me just focus on this. The size of CD, right? CD is a matrix that is M by N, right? CD gives us how many measurements we have. So, and B here is a matrix also that is N by R, where R is the number of inputs, right? So the matrix that we are going to be able to get when we do CD A to the minus 1B is actually the rows of the flexibility matrix where the measurements are and the columns of the flexibility matrix where the loads are. And that's all we can get from this formula at this point. Okay? So I think that's worthy of just one few more minutes to make sure the idea was clear. So let's say that we take a look at this, and this is coordinate 1, 2, 3, 4, 5, 6, right? Those are the degrees of freedom. Let's say that our sensors are in blue and that we have a sensor at 1 and that we have a sensor at 4 and that we have a sensor at 6. So we have measurements at 1, 4, and 6. Let's say that in addition to that, we had an input at coordinate 2. And so the excitation is in red here, was at the second coordinate. Okay, then if we look at this matrix, first, if you look at the flexibility matrix of the complete structure, would be 6 by 6, right? So it's 1, 2, 3, 4, 5, and 6 coming out, and going in 1, 2, 3, 4, 5, and 6, right? That is the whole possible thing. But what are we obtaining here? Well, we are only measuring at 1, 4, and 6. So basically our measurement row is 1, 4, and 6, right? And what is our loading row? Where our loading row here is loading row number 2. Therefore, our loading row is this one. And therefore, maybe I do blue on that one too. This is our loading row, this is our output. So since we only have the rows that are here and the columns that are there, all we have from the flexibility is that number here, which is this ball, that number there, and that number here, right? So if we compute this, we will have those three numbers. That doesn't mean, of course, we have this complete flexibility matrix, which is 6 by 6 of this structure, right? Nor does it even mean that we have anything else. We just have those three numbers, which in this case is F12, F42, and F62, right? Of the complete structure with that notation, we would have F1, 2, F4, 2, and F6, 2. That's all we would have of the flexibility matrix by applying this. So you can see that's a little bit limited, so we would like to be able to expand it, to see if we can get more out of it, right? Now you can say, well, one way you can get more, of course, is put more loads, right? So if we put loads in many more places, then we could get more of this thing, right? But applying loads is not a very simple thing dynamically. Putting sensors to measure output, it's easy. But to apply this load, we need to come in, bring a shaker, install a shaker, and so on. So loads are usually 1, if we can get away with it. And at most, 2 in some cases. Now, there are applications where there are exceptions for everything. Somebody might be thinking, I know of an application where somebody applied 20 loads. Yeah, maybe. I don't doubt it. But in general, loads are difficult and are always going to be, and most of the time are going to be just a few. Okay? So, let's see. All right. So I'm going to erase and go back to the expression that we had, which was that y sub s, without using the 0 still, is just CD times the identity times s minus a to the minus 1 times b times f sub s, right? Okay, now that matrix right here that connects the output to the input as a function of s, that is this matrix, is known as the transfer matrix. And as you can see, it's a function of s, right? So this matrix is known as the transfer matrix, and it's a function of s. Now, that transfer matrix here connects displacements to forces. There are many times where I may not be able to measure displacements, but I could only measure velocities. And much more likely, I could not measure displacements or velocities, I could only measure accelerations. So what we would like to do is to express this formula so that it doesn't matter what we measure, the formula will apply. So from here, you can see that we have that CD is equal to CV times a to the minus 1, right? And we see that CD is equal to CA times a to the minus 2, correct? Okay, so let's say that I no longer use subscript D, V, or A. I just use C. So let's say C is the output matrix for whatever we're measuring. So if that is the case, then we can say that CD is the C of whatever we are measuring multiplied times A to the minus P, where P is equal to 0 if we measure displacements, P is equal to 1 if we measure velocities, and P is equal to 2 if we measure accelerations. Because you can see that if we measure accelerations, CD would just be the C that we measured, which was CA, times a to the minus 2. Had we measured velocities, the CD would have been whatever we measured, a to the minus 1. And if we had measured displacement themselves, then C would have been the displacement, and this would have been a to the 0, which is the identity. With that in mind, then we can substitute above, and we can say that y sub s is simply equal to C, whatever we measured, times A to the minus P, multiply times the identity times S minus A to the minus 1 times B, and that is, well, times Fs. So this is the transfer matrix right here. This is the transfer matrix, which is a function of S, for whatever type of measurement you've taken, not restricted to the fact that the measurement had to be displacement. Okay? All right, I'm going to stop this for a second just to make it